Hello and welcome. In this lecture, we are going to start the chapter Motion in a Straight Line. In this lecture, we will learn about position and displacement of an object. We will learn about its average velocity and average speed. We will learn about its instantaneous velocity and speed, and we will learn about its acceleration. Now, why study motion at all? The world that we live in and everything in it moves. For example, cars are moving on the roads, objects are falling from the height, we have planetary motion, we have galactic motion, we have motion of electrons, etc. So kinematics is a branch of physics and a subdivision of classical mechanics concerned with the geometrically possible motion of a body or system of bodies without consideration of the forces involved. So in kinematics, we don't consider the cause of motion, that is force. We are only interested in the motion of the object or group of objects. Thus, kinematics aims to provide a description of spatial position of bodies, that is position and displacement, the rate of which they are moving, that is velocity, and the rate at which their velocity is changing, that is acceleration. When the causative forces are disregarded, motion descriptions are possible only for particles having constrained motion, that is, they are restricted to move along a fixed path. In unconstrained or free motion, the forces determine the shape of the path. In this chapter, we are concerned with the motion of bodies which are constrained to move in a straight line, like this dot moving in a straight line. Now, what are the position and displacement of an object? An object is located with respect to a reference point, usually the origin or 0 on an axis. Direction of motion is positive when the object moves in the positive x direction, and direction of motion is negative when the object moves in the negative x direction. Displacement from x1 to x2 is denoted by delta x, which is equal to x2 minus x1. So in this figure, origin is the reference point, x is the position, which is a scalar quantity, that means it has magnitude only. Delta x is the displacement, which is a vector quantity, that means it has magnitude as well as direction. When an object moves, its position changes with respect to time. We are interested in the rate by which the object's position changes. The average velocity of the object is defined as the displacement in the object divided by the time interval it takes to move through that displacement. This graph shows the position of an object with respect to time. Suppose in time interval delta t, the object displaces by delta x. The average velocity is thus delta x by delta t. Average speed is defined as the total distance divided by time interval. Suppose that an object moves from position x1 to x2, then moves back to x1. The displacement in this case is 0, hence average velocity is 0, but the total distance travelled is twice the distance between x1 and x2. Hence the average speed is not 0. Therefore, average velocity and average speed of an object may or may not be same. Therefore, we have two different definitions for the rate at which the object moves, that is average velocity and average speed. We have seen that the average velocity of an object moving from x1 to x2 is equal to the displacement delta x divided by time interval delta t. This is nothing but the slope of the secant line between x1 and x2. Now what happens when we start reducing delta t? the displacement delta x also starts reducing, and the secant line becomes smaller and smaller. When delta t approaches 0, the secant line becomes the tangent line of the curve depicting the position of the object. Delta x by delta t in such case is the instantaneous velocity, or simply the velocity, and the instantaneous speed is the magnitude of velocity. Therefore, instantaneous velocity, or simply velocity, is defined as delta x by delta t when delta t tends to 0. This is also represented as differentiation of position x with respect to time. Speed is the magnitude of velocity, that is, speed is velocity that has been stripped of any indication of direction. Therefore, s is equal to magnitude of v. The unit of velocity is meter per second. Now let us take an example. We are given that the position of an object changes with respect to time as half kt square, where k is any constant. We are required to find the velocity function of this object. We will solve this problem using two different methods. One is calculus method and other is method of limits. In the calculus method, we take the differentiation of the position function to get the velocity function. So we are given that xt is equal to half kt square, vt will be equal to dxt by dt. This is equal to d by dt of half kt square. Since half k is constant, we can take it outside, and derivative of t square is 2t. Therefore, vt becomes kt. This graph shows the position of the object with respect to time. This is the quadratic curve, and this graph shows the velocity of the object with respect to time. As seen from this equation, this is the linear curve. The second method that we are going to use is the method of limits. If the position of the object at time t is represented as xt equals to half kt square, and the position of the object at time t plus delta t is represented as half kt plus delta t square, the displacement is xt plus delta t minus xt, which is equal to half kt plus delta t square minus half kt square. We can expand this term and get half kt square plus 2t delta t plus delta t square minus half kt square. This half kt square and half kt square cancels, and we get half k 2t delta t plus delta t square. Now we know that vt is equal to delta x by delta t when delta t tends to 0. Therefore, vt is equal to half k limit delta t tends to 0, 2t delta t plus delta t square divided by delta t. This is equal to half k limit delta t tends to 0, 2t plus delta t. Since delta t tends to 0, this can be neglected, and we get vt is equal to half k times 2t. This is equal to kt. In the previous example, we have seen that the velocity of an object can also change with time. When the velocity of the object changes, it is said to undergo acceleration. The average acceleration over a time interval delta t is therefore A average is equal to delta v by delta t. The instantaneous acceleration, or simply acceleration, is A equals to limit delta t tends to 0 delta v by delta t. This is equal to dv by dt, and which is in turn equal to double derivative of position, that is d square x by dt square. The unit of acceleration is meter per second square. Now let us take an example. An object's position is given by xt equal to 4 minus 27t plus t cube. We are required to find vt and at. So we are given that xt is equal to 4 minus 27t plus t cube. We know that vt is equal to dxt by dt. Therefore, vt is equal to d by dt of 4 minus 27t plus t cube. Since d by dt of a constant term is 0 and d by dt of 27t will give 27 and d by dt of t cube will give 3t square, we get Vt is equal to minus 27 plus 3t square. We also know that the acceleration is the derivative of velocity. Therefore, acceleration is d by dt of minus 27 plus 3t square, which is equal to 60. The graph shown here shows the variation of position, velocity and acceleration with respect to time. The position changes cubically, velocity changes quadratically, and acceleration changes linearly, as we have got from these relations. Let us take another example. In this example, we are given the position plot of an elevator cab that is initially stationary, then moves upward and then stops. We are required to plot Vt and At. So velocity plot and acceleration plot according to the position plot is shown here, and the plots are divided into different sections. In section A, position is 0, therefore velocity and acceleration are also 0. In section B, position is changing with proportional to time square, therefore velocity is changing proportional to time and acceleration is constant. In section C, position is proportional to time, therefore velocity is constant and acceleration is 0. In section D, position is again changing with respect to time square, therefore velocity is proportional to time and acceleration is again constant in the negative direction. In section E, position is fixed, therefore velocity and acceleration is 0. So far in this lecture, we have learned about the position and displacement of an object. We have learned about the average velocity and instantaneous velocity. We have learned about the acceleration of the object. In the next lecture, we will learn about the special case of uniformly accelerated motion. We will learn about relative velocity, and then we will take some problems and their solutions.